Welcome to a second example of quadratic regression. Again, the goals are to perform quadratic regression on the TI84 graphing calculator, determine how well the regression model fits the data, and then make predictions using the regression equation. So to perform the regression analysis, we're going to create a scatter plot of the data. If the data fits the pattern of a quadratic function as we see here below, we can use a quadratic equation to model the data and then make predictions. So let's go and take a look at our second example. In this example, we have data from a ball that's thrown comparing the horizontal distance to the height of the ball. So the first thing we'll do is we'll plot the paired data on the coordinate plane and see if the pattern fits the shape of a quadratic function. But first we have to scale our x and y axes to make sure all of the data fits on the coordinate plane. Notice the horizontal distance is from 0 to 50. So we first label the x-axis as the horizontal distance in feet, and the axis must include, so we'll go from 0 to 50, scaling it by tens. And then for the height, the smallest value is 5, the largest value is 20. So let's scale the y-axis by 5s from 0 to 25. And now we'll go ahead and plot the points. 0, 5, 10, 8, 20, 12, 30, 20, 40, 15, and 50, 10. So we can see the data does rise and then fall. So a quadratic function may fit this data pretty well, even though it doesn't look very rounded like most parabolas. But we can go ahead and perform quadratic regression and then using R-squared determine how well the equation fits the data. So let's first duplicate this scatter plot on our graphing calculator. To enter the data, we'll press Stat Enter. We'll clear out the old data by going to the top of the column, pressing Clear and then Enter for L1 and L2. So L1 will contain the x values, and then L2 will be the y values. Now let's set up the x and y axes by pressing the window key. And again, the y values must go from at least 0 to 50. Let's go from -5 to 55. X scale will be 5s. Then for y, we'll go from -5 to 25 by 5s. Let's make sure the scatter plot is turned on. Press second y equals. Notice here it's already turned on, but if it wasn't, you would just press Enter and then press Enter while the cursor is on. The scatter plot option is selected. X and Y are L1 and L2. Let's go ahead and press Graph. And this scatter plot resembles the one we did by hand. Now we're going to go ahead and perform regression to determine the quadratic model, but we also want to make sure that R-squared is going to show on the screen. So let's make sure our diagnostic tool is turned on. We're going to press second 0, scroll down to D, and look for diagnostic on. Here it is, so we'll press Enter and then Enter one more time. And now we'll perform quadratic regression by pressing Stat, right arrow once. Option 5 is quadratic regression, so we'll press 5. Now before we press Enter, we want to automatically store the equation in Y1. So we're going to press the vars key, right arrow once, Enter, and then Enter. And this will automatically store the regression equation in Y1. So now we'll press Enter. Here's our model. Notice R-squared is 0.78, and the closer this value is to 1, the better the model. So it's a decent model, but it's not an excellent model. This tells us that approximately 78% of the variability of the data can be explained by this model. If we press Graph, we can visually see how well this function fits the data. And again, it's not a great fit, but it's a decent fit. So we could make some predictions using this model. Let's go ahead and write down our function, and we're going to round to 4 decimal places this time. Now let's see if we can answer these questions. Number 1, it says, what is the initial height of the ball? Well, going back to our data for a moment, the initial horizontal distance occurred when x is equal to 0, and the vertical height was actually 5 feet. But according to our model, when x is equal to 0, the initial height is approximately 3.3 feet. And this is just an indication that our model is not perfect. We can see right away there's a margin of error for the initial height of the ball. So according to the model, the initial height would be approximately 3.3 feet, but the actual initial height was 5 feet. This is important to keep in mind because whenever we use a model, there's usually going to be a margin of error. Number 2, what would you predict the height of the ball to be after traveling 55 feet? Well, 55 feet is a horizontal distance, so we want to determine what y would be when x is equal to 55. We'll go ahead and use the table feature of the calculator to answer this question. This is one of the benefits of storing this equation in y1. Let's make sure our table is set up correctly. We press second window. We'll go ahead and have our table start at 0 and increase by 1s. Now if we press second graph, we can just scroll down to x equals 55 and see what the y value would be. Well, according to our model, at a horizontal distance of 55 feet, the height would be approximately 8.0 feet. Number 3 asks us how far will the ball travel? Again, let's go back and take a look at our initial data. If we want to know how far the ball is going to travel, we want to know when the height is equal to 0, or when the ball hits the ground, what would the horizontal distance be? So now we want to determine what x would be when y is equal to 0. And again, we're going to go ahead and use the table feature of the graphing calculator to answer this question. Let's go ahead and keep scrolling down until we have a y value that's equal to 0. We can tell from the table somewhere between x equals 65 and x equals 66, the y value would have to be 0. If we need more accuracy than that, let's go ahead and take a look at the graph of our function. Let's go ahead and extend the x-axis so we can see when this ball will hit the ground. So I'm going to change the y max to, let's say, 80 and see what that does. Now we can see, according to our model, the ball is going to hit the ground at this x-intercept. Let's go ahead and calculate this. We'll press second trace. X-intercept would be a 0 of the function, so we'll press 2. Let's move closer to the x-intercept, but stay to the left side because it's asking for the left bound. Let's press enter. Now we'll move to the right side of this intercept, which should be below. Press enter. When it says guess, we'll go ahead and just move the cursor a little bit closer. We'll press enter one more time. So we can see the horizontal distance, or the distance the ball would travel, would be approximately 65.1 feet. And the last question, do you believe the quadratic function is a good model for this situation? Why or why not? So this is kind of open-ended. We can see visually it's not the best model in the world, and we did have an r² value of approximately 0.78, and the closer this value is to 1, the better the model. So I would venture to say that it's a decent model, but we would prefer r² to be a little bit closer to positive 1. So I'm going to go ahead and leave that answer for you. I hope you found this video helpful. Thank you for watching.